Alrighty, so for this video, we're gonna do number 4 on page 6, parts B and C for exam number 2, which is in relation to derivatives. So in this case, for part B, so we have function g of x equals x secant x minus cosine of tangent of x to the power 4 minus inverse of sine of 1 over x. So in this case, we want to start by taking each individual term, each within the expression, piece by piece. So in this case, we have u and d, so we can apply the product rule because we have two terms that are being multiplied with each other. So the product rule, once again, it's always going to be u prime times v plus v prime times u. So in this case, u prime is just 1. Times v, which is just secant of secant x, plus v prime, which is just secant tangent x. Times u, which is just x. So this should give us the derivative for the first term. And then the second term, which is cosine of tangent of x to the 4. So in this case, we would have to use the chain rule. So by using the chain rule, we first find the derivative of cosine, which is just negative sine of tan to the power of x, of tan of x to the power 4 times the derivative of the inside, which is just secant squared of x to the 4, and then times the derivative of the inside, which would just be 4x to the power 3, because we're utilizing the power rule. So in this case, we bring down the 4, and you have 4x, and then you subtract 4 minus 1 to get the new power, which is 3. So put that into big parentheses. And then lastly, we have inverse of sine of 1 over x. So in this case, we can just use the same chain rule. So the derivative of sine of inverse sine of 1 over x, which is be 1 over square root of 1 minus 1 over x squared, times, because this is a chain rule, so we have to multiply the initial derivative times the derivative of the inside. So the derivative of the inside in this case would just be negative 1 x squared, or negative 1 over x squared. So we have the two big, the three big terminologies over here. So typically it would be nicer to combine a little bit. So in this case, we can just combine it all into a giant derivative function. So 1 times secant x is just secant of secant x plus secant x tan x. And then given that we have given that we have two negatives over here, we can just say plus, or in this case we can just, if we're writing parentheses, we just say minus, and then minus negative 4x to the third sine of tan of x to the power 4 times secant squared of x to the 4. which would give you the whole entire derivative. So the result would just be this big derivative expression right over here, which should just give you the derivative of the whole function. You could probably simplify it even further if you'd like, but honestly, in these kinds of instances, it would probably be best to just leave it as that in order to not complicate yourself. And like typically, you're not asked to simplify it down even further, but I mean, it's totally up to you, but I would highly recommend to do that. Okay, and then now moving on to part C. So in part C, we have the expression h of x equals e to the power of negative x plus 2 plus ln of cotangent x minus log base 2 of 5x. So as we did in the first part of this problem, we want to take each term bit by bit. So we have 3 terms over here. So we have number 1, number 2, and number 3. So we want to first find the derivative of this term, and the derivative of anything e to the power of a function, it's always going to be e to the, or for example, if you have e to the u, it's always going to be e to the u times prime u. So that should give you the derivative for this one. So in this case, the derivative would be e to the negative x plus 2 times negative 1. That's going to give you the derivative for this one, because you have the whole original function that we took earlier times negative 1, and negative 1 is the derivative of the exponent function, because the derivative of 2 is always just going to be 0 because 2 is a constant. So the derivative of any constant is going to be 0, and then the derivative of negative x is just going to be negative 1. That's it, because you have x to the power of 0, and then you subtract that, or you bring down the 0. No, you have x to 1, you bring down the 1, and then you would have 1x to the power of 0. X to the power of 0 is just 1, so negative 1 times 1 is just negative 1. So that should just give you the derivative. And then, now going on to the second term over here, so we have ln of cotangent x. So that, anything ln is always going to be 1 over the term for the derivative. So in this case, it would just be 1 over cotangent x. But given that this is the chain rule, because we have a function, we have a trig function inside of the natural log, we would have to multiply by the derivative of cotangent x, which is just cosecant squared in this instance. And then you probably want to put some parentheses around it, just to like make it easier for you to distinguish, where you're at and like what kind of terms you're working with. And then lastly, for the last derivative over here, so we have log base 2 of 5x. So the derivative of that can always be, of any log, can always be attributed to, for example, if we take log b of x, so that would just always be 1 over x times ln of b. That's always going to define the natural log for this. So in this case, given that we have this base formula for the derivative, so we can take this concept and apply it to the log over here. So in this case, the derivative would just be 1 over 5x ln of 2, because 2 is our b in this case. But the problem is, or not the problem is, but the additional idea to consider is that given that we have a function inside of the log, we have to use the chain rule, which means that we would apply the initial derivative to the log, but then we have to multiply by the derivative of the inside function, which would just be 5 in this case. So now we have the new free derivative terms right here. And now we can try to combine them together. So in this case, right here we'd have negative e to the power of negative x plus 2 minus cosecant squared x over cotangent x. And then right over here, we will just probably have minus 5 over 5x ln of 2. And you want to make sure you put parentheses around the 2 when it comes to the ln. So this right here should give you the final simplified expression for the derivative of the evaluated term, or the evaluated expression over here. So yeah.